this is a subject that we've been working on for the past 8 years. We're bringing new technology into the market that is advancing in energy efficiency relative to gas turbines, and then in future generations, likely steam turbines as well too. So as Greg said, my name is Jim Hannon. I'm ExxonMobil's lubrication technology advisor, supporting our turbine oils. And I've been in this role for the past 13 years and 30 plus years in the power generation industry. So appreciate the ability to continue working on things that I thoroughly enjoy. So the idea of improving energy efficiency through lubrication actually was a combined effort between ExxonMobil and General Electric, as General Electric reached out to ExxonMobil probably about 8 years ago now, and asked if we had ideas on technology to make advancements, and their direction and their thinking was to reduce viscosity to make that happen. And as we started digging deeper, we learned it's a lot more than just the viscosity, and we'll show you how we understand that and the details of that. But my slides aren't advancing. There we go. Okay. So what I'm hoping for you to have some key takeaways from today's talk is that we want to talk to you about the science behind the influences on energy efficiency. We want to give you the understanding of the work we have done in both the field and the lab to confirm these energy savings that we have seen. We also want to talk to you about the reliability aspect of things. It's no good having a more efficient turbine if your equipment doesn't get the oil life and the equipment life as you have seen today. And then lastly, we want to show you how this translates to the bottom line. Any improvements have to have a justifiable economic impact, and we're hoping to demonstrate that today in some of the modeling that we've done. So as I mentioned, we started out with GE, and GE in turn developed a new specification specific to energy efficient turbine oils. And this is the GEK 121603 specification. And we'll talk a little bit more about that coming up. But what we understand from our testing, both in the rig and in the field, is with the efficiencies we expect to see, here's some nominal savings that we might see. And so the $39,000 a year or on electrical savings, that actually is electricity that you can produce, sellable electricity, in addition to the electricity that GE Frame 7 FA, for example, would be able to produce, and or the reduced fuel consumption, the $9,200 per year in reduced fuel consumption. It is based on a few assumptions. So it's based on a GE Frame 7 FA03 169 megawatt gas turbine running at 5,000 hours. So if your equipment is running greater than 5,000 hours, you'd expect to have better performance, better economics. The heat rate of 8,839 BTU per kW, that's basically the efficiency of that turbine. And then the electrical rate, the cost to produce electricity at 5.67 cents per kW. The gas consumption savings are based on $2.50 per million BTU. So that's the kind of attraction, is we see savings on gas consumption and savings on, or actually additional revenue based on the ability to produce more electricity. So the GE spec that we worked on with GE is this 121603, and it's a very detailed spec. We have an exclusive endorsement at this point in time, and one of the key parameters within the spec is that the energy efficiency claims must be confirmed by GE approved rig testing and GE approved gas turbine field demonstrations. And then any equipment that has a gearbox, the gearbox manufacturer must confirm the appropriateness of the oil. So those are some stipulations as to being able to use this this oil per the GE standard. So when you're looking at a gas turbine, and this is an example of a GE Frame 7 FA gas turbine, they often call it a 4-bearing machine. So on the left-hand side is the gas turbine part of the turbine, and you see you've got your, further to the left is the bearing. It's a tilt pad bearing in the combustion section holding up that part of the shaft. And then as you progress to the right, you'll see the air compressor section, and that's another tilt pad bearing. And then we get to the generator section that are the elliptical bearings. And so again, it's a 4-bearing machine. What we've seen down in the blue box is from our testing, we see a bearing power loss reductions in the area of 15 to 16% in each bearing. So we take the horsepower loss that's currently fairly efficient at 0.5320 horsepower, and then reduce that to 0.4505 horsepower. This is a heat rate reduction of 0.08%. And you can see that heat rate that goes from the 8839 down to the 8832 BTU per kW. That improvement in heat rate yields 136 kW of more energy output that's not wasted in heat loss. So you could think of it as free power. Another benefit too is now that you've got more electricity for less fuel coming in, you would see some environmental benefits as well too, because of the efficiencies gained there. So in the development of this oil, we first looked at experimental formulations, and then we did some GE rig testing, and we'll talk to you about that rig. We then worked the GE test stand to confirm, and then we also did field demonstrations. So we had multiple layers to confirm that we were seeing the improvements we expected. And then lastly, in field demonstrations, we were able to confirm, in real life. And the biggest thing is to be able to continue to maintain that reliability that we expect from an ISO 32 oil. So you can see we're going from a traditional 32 centistoke oil to an 18 centistoke oil. And when we did that, we had to look at these 4 key parameters: the volatility of the oil, the flash point of the oil, the specific heat of the oil, and the density of the oil. All of those had key elements as to drive what base oil and additive technology was best suited for this application. So in the GE test stand, GE had designed this and fabricated through a third party to replicate what we would see in a GE Frame 7, or actually even in the GEH models, on a 4-to-1 ratio of bearing size versus speed, And what they did was they would put an artificial load on the bearing and then run it at various speeds and to confirm the efficiencies. So we went through 6 different oils, and we followed what is called ASTM 7721 test protocol, where we followed the AB method. So we tested oil A, then oil B, then oil A again, and then oil B again. This allowed us to compare that the A's were the same and the B's were the same. If we had any divergence in data, we knew that that there would be something that would indicate something was in error with the test rig. So we didn't have any of that. Our A's always matched up and our B's always matched up. And it did tell us quite a few interesting things. In particular, we had a lower viscosity oil that we liked quite a bit. One element of it, it was a higher density, and that did not test out as well as the oil that we finally decided on, the 18 centistoke oil. We then went to GE and had a discussion about putting it in the GE test stand down in Greenville, South Carolina. And this was a significant achievement to get it into this multi-million-dollar test stand on a multi-million-dollar piece of equipment. And this was a GE Frame 7 HA turbine. And this is running, and the oil is still in use today in their test stand. But we were able to confirm a few key things. One is that we saw no significant difference in vibration or temperatures at the critical speeds. We did see bearing metal temperature reduction that helped confirm our energy saving predictions, and that further confirmed that 16% energy savings in each of the bearings. Then we took it to the field, and this is a GE Frame 7 FA03 turbine. And what you can see is the data from the ISO 32 oil, and we've got the gas turbine section and the generator section, and we look at the #1 journal and thrust bearing horsepower requirements, then the #2 journal bearing horsepower requirements, and then the generator drive end and collector end horsepower requirements. And then we applied the energy efficiency. We were able to confirm the energy efficiency savings through change in temperature at the bearing, from the bearing inlet to the bearing outlet, and then saw the savings as seen on your screen here with the ISO, or the 18 centistoke oil. And you can see collectively the horsepower drop was from 1,206 horsepower down to 1,022 horsepower, and that is that 15% savings. That also generated the additional 136 kW of what we would call free electricity. So those were the 3 key areas of confirmation: the low loss bearing rig test with GE and a third party, the GE test stand, and now we have 2 GE field demonstrations in the GE Frame 7 FA turbines. So then back to the big question: does a lower viscosity oil temperature improve bearing efficiencies? And the first thought, like in the automotive industry, is yes. But as you dig deeper, you'll see that it's actually the influence of your dynamic viscosity and your specific heat that is driving those efficiency gains. So the dynamic viscosity is strongly influenced by density. And so the density of that oil is a key element that is driving the reduced energy consumption in a bearing. Then in parallel, specific heat is also a key driver to improve energy efficiencies. And you can see the heat balance calculation below that identifies the specific heat there and BTU per gallon degree F. And in the next slide, I'll show you the influence that has in running these energy efficiency calculations. So when we go for a lower dynamic viscosity and lower specific heat, we end up with a lower, we end up improving our energy efficiency. So here's a power loss example. And here's our ISO 32 oil, and you can see the flow rate, the delta T at 24, the specific heat, the dynamic viscosity, the horsepower loss calculated, and then a comparison that we'll compare to the other products now. So this is comparing it to an 18 centistoke oil. Same flow rate, a lower delta T. Instead of 24 degrees, we're now at 21 degrees, and we've been able to confirm that in these GE Frame 7 FA examples. You can see the specific heat difference. You can see the dynamic viscosity is lower, and therefore the horsepower loss is lower, and then the overall efficiency gain in that bearing is 14.7%. We did another example of a water-soluble PAG oil, same flow rate. We assumed the same delta T, assuming you did see some improvement on temperature, but the influence on specific heat and dynamic viscosity, both being higher, actually attribute to a higher energy loss. So you can see the horsepower loss goes to 1,205 horsepower. So we've actually had a gain in horsepower of negative 1.4. So through all of this, we also need to bear in mind the reliability of the equipment. And when we took this opportunity to our in-house plant in Beaumont, where they have a GE Frame 7 FA, we went through a very rigorous and detailed process of risk management. And through this, we identified 43 components of concern or interest, and then we identified the potential concern, what the resolution, what the technology risk assessment was, whether there was any mitigation and any follow-up actions. And through that, we line by line looked at everything from the lube oil lift pumps to the hydrogen seals, to the actuators, and to the lube oil pumps, just to make sure that there was no negative implication of going from 32 centistoke to 18 centistoke. And at the end of the day, we were able to vet that and confirm with a high degree of confidence that we would not see any negative impact in operation. And so that was installed in our turbine back in July and has been running since then. The other GE Frame 7 FA has been in operation for over 2 years, and we follow up with the customer, and they're quite pleased. And as a matter of fact, have now, as we speak, are loading in a second load into their sister GE Frame 7 FA turbine. So, in conclusion, I wanted to drive to the economic benefit of this. We do see $39,000 per year of incremental sellable electricity that with just an oil change. We can see a $9,200 reduction in fuel consumption per year. And then lastly, the environmental benefit of 455 ton reduction in CO2 based on these efficiency gains. This is again based on that 5,000 hour a year operating model. So I will have a little bit of time at the end. I did want to just offer that you can learn more about energy efficiencies at mobile.com efficient turbines. I did want to also offer that this was brought to you by some other key collaborators in Mike Galloway from our equipment builder group, and then Charlie Smith from our marketing team. And we have been pressing this for a number of years now and are very happy to be at a point of commercialization.